Derive the Lagrange equation for non-holonomic system with moving constraints. Solution. Let us consider a system of n particles with masses mi and position vector ri. Also, let Fi be the total force acting on the typical particle. Let Ri dot be the function of the Q1, Q2, Qn and T, that is Ri is equal to Ri bracket starts Q1, Q2, so on Qn and T bracket close. Here the time T is the included to allow for moving constraints, that is holonomic system. Therefore dri upon dt is equal to ri dot, which is equal to sigma j varying from 1 to n del ri upon del qj dot plus del ri upon del t. Now differentiating the partially with respect to qk, we get del ri dot upon del qk is equal to sigma j varying from 1 to n del square ri upon del qk del qj into qj dot plus del over del qk bracket starts del ri upon del t bracket close, or del ri dot upon del qk is equal to sigma j varying from 1 to n del over del qj bracket starts del ri upon del qk bracket close qj dot plus del over del dt del t bracket starts del ri upon del qk bracket close, or del ri dot upon del qk is equal to d over dt bracket starts del ri upon del qk bracket close, which is equation 2. Now differentiating one partially with respect to qj, we get del ri dot upon del qj dot is equal to del ri upon del qj. The kinetic energy of the system is given by T is equal to half sigma I mi bracket starts ri dot into ri dot bracket close. And differentiating equation 4, this is equation 4 T with respect to partially with respect to qj dot, we get del over del t qj 1 upon half sigma mi bracket starts m del ri upon del qj ri dot plus ri dot into del ri dot upon del qj dot bracket close, so which is equal to sigma I varying from mi ri dot del ri upon del qj dot, which is equal to sigma varying from I m I ri dot mi ri dot del ri upon del qj square bracket, because sigma ri dot upon del qj is equal to del ri upon del qj by equation 3. So we get therefore du dt bracket starts del t over del qj dot bracket close is equal to sigma I mi ri double dot del ri upon del qj plus sigma mi ri del ri dot upon del qj, which is equation 5. Now also differentiating 4 with respect to qj, we get del t over del qj 1 upon half sigma I mi square bracket starts del ri dot upon del qj ri dot plus ri dot into del ri dot upon del qj square bracket close, which is equal to sigma I mi ri dot del ri upon del qj, which is equation 6. Now let us now define the sj by sj is equal to d over dt bracket starts del t over del qj bracket closed del t over del qj. Now putting the value of d over dt or del t over del qj from 5 v and del t over del qj for from equation 6 into 7, we get sj is equal to sigma mi ri double dot del ri upon del qj sigma I mi ri dot del ri upon del qj sigma I mi ri dot del ri dot del qj, which is equal to sj sigma varying from I mi ri dot double dot del ri upon del qj, which is equation 8. Now by D'Alembert's principle, we have sigma mi ri double dot minus fi is equal to delta ri is equal to 0, where delta ri is equal to sigma j varying from 1 to n del ri upon del qj delta qj. Now putting the value of delta ri from equation 9, delta ri from this equation 9, value of delta ri in equation 9, we get sigma j varying from 1 to n square bracket starts sigma I bracket starts mi ri double dot minus fi del ri upon del qj delta qj bracket close square bracket close is equal to 0. So which is equal to, or j varying from 1 to n square bracket starts sigma I mi ri double dot del ri upon del qj square bracket close delta qj minus sigma j varying from 1 to n square bracket starts sigma I fi delta del ri upon del qj square bracket close delta qj is equal to 0, or j varying from 1 to n square bracket starts sigma I mi ri double dot del ri upon del qj square bracket close delta qj j varying from sigma j varying from 1 to n square bracket starts sigma I fi del ri qj square bracket close delta qj, or which is equal to sigma j from 1 to n del qj delta qj is equal to sigma j varying from 1 to n qj delta qj, where qj is equal to sigma fi del ri upon del qj is the generalized force, or sigma j varying from 1 to n sj delta qj is equal to sigma j varying from 1 to n qj delta qj is equal to 0, or sigma j varying from 1 to n sj qj sj minus qj is bracket close delta qj is equal to 0. If delta qj were arbitrary, we would conclude that sj is equal to qj in the same as the Lagrange's equation for a simple dynamic system. Now we consider a new class of constraints which does not restrict the motion of the particle to a surface but to the domain of the bounded by the surface. They are known as the inequality of the constraints and are of the form of f is equal to bracket starts q1 q2 so on qn and t bracket close which is greater than 0 if the boundary of the surface is in the motion, then it corresponds to the non-holonomic system constraints. These constraints can be generalized by the defining a system of n dependent generalized coordinates of q1 q2 and so on qn, but the relativity by m constraints of the form sigma j varying from 1 to n alpha j d qj plus d alpha dt is equal to 0, alpha varying from 1 to and m is less than n, which is equation 10, where a is a function of the qj's and t. Also, the possible displacement of qj satisfy the equation 10, while the virtual displacements satisfy sigma j, alpha j, delta alpha j is equal to 0, alpha is equal to 1, 2 and m, which is equation 11. Multiplying the equation 11 by lambda 1, lambda 2 and so on lambda m respectively, such and subtracting from 9, we define f by f is equal to bracket starts s1 minus q1 lambda 1 a 1 1 minus lambda 2 a 2 1 minus so on lambda m a m 1 bracket close delta q1 plus bracket start s2 minus q2 minus lambda 1 a 1 2 minus lambda 2 a 2 2 so on lambda m a m 2 bracket close delta q2 plus so on bracket starts sn minus qn minus lambda 1 1 n minus lambda 2 a 2 n so on lambda n a m n delta q n, which is equation 12, taking sj and qj is equal to bj and 12 is written, equation 12 is written as f is equal to bracket starts beta 1 minus lambda 1 a 1 1 minus lambda 2 a 2 1 and so on am lambda m a m 1 bracket close delta q1 plus small bracket starts beta 2 minus lambda 1 a 1 2 minus lambda 2 a 2 2 so on minus lambda a m 2 bracket close delta q2 plus so on plus bracket starts bn minus lambda 1 a1 n minus lambda 2 a 2 n minus lambda m a m n bracket close delta q n. Let us choose the lambda to satisfy the equation m equations. So beta 1 is equal to lambda 1 a1 plus lambda 2 a2 plus so on lambda m a m1 and beta 2 is equal to lambda 1 a1 2 lambda a2 2 and so on plus lambda m am 2 and lambda m is equal to lambda 1 beta m is equal to lambda 1 am1 plus lambda 2 am2 and so on lambda m amn, which is equation 13. so that f reduces to f is equal to bracket starts beta m plus 1 lambda a 1 comma m plus 1 minus so on lambda m a m comma m plus 1 bracket close delta q m plus 1 plus beta m plus 2 lambda a 1 m plus 2 so on lambda m a m m plus 2 bracket close delta q m plus 2 plus so on plus bracket close beta bracket starts beta n lambda 1 a 1 n minus so on lambda a m lambda m a m n bracket close delta q n, which is equation 14. Now equation 14 must vanish for the arbitrary value of the delta q m plus 1 delta q so on delta qn, since when there is a values are given we can always choose delta q1 delta q2 delta q so on delta qm to satisfy in the equation 11. So f is equal to 0, therefore we have beta m plus 1 is equal to lambda 1 a1 comma m plus 1 lambda 2 a2 m plus 1 so on plus lambda am lambda m am m plus 1 beta m plus 2 is equal to lambda 1 a1 m plus 2 plus lambda 2 a2 m plus 2 plus so on lambda m a m m plus 2 and so on, and beta n is equal to lambda 1 a1 n plus lambda 2 a2 n plus so on plus lambda m a m n. Now the combining the equations 13 15 we get sj minus qj is equal to bj alpha 1 1 to m lambda alpha j is 1 to n or sj is equal to qj plus alpha varying from 1 to m lambda alpha j comma j 1 to n, or du or dt of bracket starts del t over del qj dot bracket close del t over del qj is equal to qj alpha varying from 1 to m lambda alpha j varying from 1 to n, which is equation 16. So these are the Lagrange's equation of motion for a rheonomic non-conservative and non-holonomic system. So lambda 1 lambda 2 are called as the Lagrange's multipliers of equation 10 and 16 together constitutes the n plus m equations, and these n plus m equations are solved for the n plus m equations of q1 q2 and qn lambda 1 lambda 2 and so on lambda m. So this is the Lagrange's equation for non-holonomic system with moving constraints.